welcome to the next part of a series RLC AC circuits helper video. So I just wanted to add that, yes, there was a little decimal place issue in here where we just needed a 1 in there. So my next example question is to introduce you to the next type of reactance, which is AC equivalent resistance for the capacitor, which is given the symbol XC. So that is capacitive reactance. Okay, why are we calculating this sort of thing? Because we need it to do our calculations for our voltage phasor, which is going to come up on the next question. So we need to know these values. So what we'll do is we're going to do a calculation for XC. Okay, this time the formula is, so as the capacitance and the frequency increase, the XC would decrease, and the other way around, vice versa. So that is 1 over 2 pi FC. So in this particular question, if we look on our circuit, then this is, you'll notice that this is 1 over 2 pi, and its times frequency this time for those that are observant is 60 hertz, and it is times 20 microfarads. The unit of capacitance is times 10 to the minus 6 this time. So it's a 2 times shift pi times 60 minus 6. That should be correct. Right, so that equals that, and then we're going to do a 1 over, and that equals that, 132.629. And that is in ohms as well. Okay, so we can now move down to a phasor type question. So this is a combination of a resistor and an inductor in this circuit. Okay, so we need to be able to work out the phasor diagram for this. So we can actually this time do an impedance phasor diagram, and everything lines up with the civil acronym still. Okay, so we start from a reference point, and we are going to do, so the resistance would go out to the right here, and that is 100 ohms. And maybe move that along a little bit so it doesn't interfere with it, because that is going up. Right, so, and again, actually I could have done it with the, I'm just going to do it with the drawing to start with. So if we were to work out, did we work out the 10 micro henries from above, which is millihenries? Yep, so that is, we've worked it out there. So we just draw the arrow up. So our rotating phasor will go up here, and it is 3.14159 ohms, and that is XL. Okay, equals. Right, so if we wanted to work out the resultant AC resistance, and there is a name for that, the resultant AC resistance is called, it's given the symbol Z, and it's called impedance. So that is the total AC resistance in the circuit. So now if you wanted to work out what Z was, we would use the same method by doing a resultant vector here from the phasor diagram, and this angle here would be equal to the phase angle. So we have just drawn a right angle triangle. So we are able to that's Z there, calculate that using Pythagoras' theorem. Z squared, the large side, is equal to XL squared plus R squared. So that is 3 pi. It's best to really keep that in your for accuracy. Keep that in there as pi squared plus 100 squared. So Z is equal to the square root inverse function of pi squared plus 100 squared. So if we put that in the calculator, plus 100 squared equals. Right, so then we need to do the square root. Answer equals that. So that is 100.049. 100.049, and that is in ohms. Whoops. Okay, that's good. So now what we can do is you notice the current is labeled on there, I. Right. Okay, so now we can work out the current, and we can work out the current using a Ohm's law style formula. So V divided by Z, and the V is actually the resultant supply voltage, which is given in there as 240 volts. Now when it's written as 240 volts on the question like this, the supply, it generally means RMS, which we've talked about before. If you're given that in peak, you'd have to convert it. 240 divided by Z, which is 100.049, and that will give you your answer for your current. 399 amps. Good. So if the question was asking for the current, that's what we would find for that. So you may have noticed that we do have the voltage as well in there. So we should be able to find out the voltage across both the resistor and VR, and we should be able to find it across the inductor VL. So one thing that we could do, and we haven't found yet, is to work out the phase angle. So phase angle. So we notice that that is labeled in the triangle there. So we've got several. We can use, obviously, trigonometry is the best option here. So we can do it with any of those trig SOHCAHTOA type ratios. So let's use tan. So tan of the phase angle equals opposite over adjacent, TOA of SOHCAHTOA. And so opposite there is basically pi, isn't it? Pi divided by adjacent, which is 100. So we're going to do an inverse tan of that to get the angle. So tan inverse of the ratio of that will give me the angle. So let's do that on here. We do shift pi divided by 100, which is fairly straightforward. And then we're going to do an inverse tan. So we do shift, that one, answer equals. There we go. And that should be in degrees. So that, what was it? 1.799. 1.799 degrees. We can take this diagram, copy it down to here. Before we do that, insert space, right. Copy down here. Right, this time, so we know we are dealing with a voltage phasor. So this is going to be, so the VS is going to be 240 volts. And okay, then this diagram a bit bigger. So the phase angle here, we just calculated, is 1.799 degrees. So we can find out, using trigonometry again, what V, that is VR there, and this is VL. So let's do cos. So cos of the angle equals adjacent over hypotenuse, K. So we have, and we're trying to find out, so let's put these values in. So adjacent is VR divided by VS, which equals VR divided by 240 volts. Okay, so we do cos of 1.799 multiplied by 240, because we multiply both sides by 240, equals VR. So VR, if you put it in a calculator, should give us the answers. 1.79, so that is cos, bracket equals, and then we're going to times it by 240. 240. 239.88. 239.88 volts. And we can now work out what VL is by doing, I would do Pythagoras. Square root of the big VS squared minus VR squared. So that is 240 squared times by 239.88 squared square rooted. Let's do that. Look at that, we've still got it up there. Squared times, did I say times? No. Minus. Good way of checking. So answer squared minus, do we have XY on here? Can we move back? Of course you can. 240 squared minus, yes, okay, which gives us that, and then square root is that one, answer equals 7.536. 0.536 volts. Yep, that's it. So that concludes the last calculation. I mean, we could put that on there now. Actually, let's put it in the diagram. So VR equals 239.88 volts, and this one here equals VL equals not as much, 7.536 volts. Very good. So, and then we could have put the current on there as well, which we've also worked out. And we could highlight those as well, so it's clearer on here. And the phase angle. And the current. And that is a series circuit with an inductor and resistor in it. I'm going to stop there until the next video, which will include a capacitor calculation.